Hello everybody. Today I want to talk to you about the stellar evolution and formation of stars, and now I will share my screen. Yes, the structure and evolution of stars. You see here, here we have, for example, two stars, and we want to see that which one is more luminous. For luminosity, we have, for example, this star with this radius. They are in the same radius, but the temperature is different. For example, this one has more temperature. So, how is the luminosity between them? What is the difference? And I will answer you later. If we have two stars with different radius. For example, this star has two more radius than this star. How is the luminance between them? Okay, we see that for each centimeter square of each surface emits the same amount of radiation. If we have the larger star, it emits more radiation because it has a larger surface. It emits 4 times as much radiation. With these stars, for example, we have this formula that luminosity is proportional to radius and temperature, with radius to power 2 and temperature power 4. And if we have a star and it's 2 times as hot as star B and the same radius, then it will be 2 to power 4 or 16 times as luminous. So you see that luminosity is proportional to power 2 of radius and power 4 of temperature. And now the question is, where do stars form? In bulk globules for low mass stars. For example, in here you see that the Rosette Nebula, that we have some stars that will be formed in radius less than 1 parsec, and mass less than 1,000 sun, mass of the sun. And the temperature is 10 Kelvin. What does it mean? It means that we have no flux in infrared and X-ray and no radiation. So the temperature is 10 Kelvin, which is low and cold, and we cannot observe in visual wavelengths. The other thing is that we can see that the stars form in giant molecular clouds, that the radius is between 10 and 100 parsec, and mass is up to a few 10 to power 6 or 1 million sun. And temperature is again around 10 Kelvin, which is low and cold. And here you see the Eta Carinæ Nebula, and here you see the Eagle Nebula. We have things that we call it genes length. When does gravity win? We can see that, for example, we have n molecules of mass m in a box of size L. Just pay attention that here L is not luminosity. L is related to length or size. And at the temperature of T, we have gravitational energy, and you see the thermal energy, and NKT, K is the Boltzmann constant, and we have the total mass, Nm, and the ratio of gravitational energy and thermal energy, and genes length, and gravity wins when L or length is more than the length of genes or genes length. And here we have genes length, as I told you already, is in this formula, and genes mass we can say that the lowest Jeans mass for it is for cool with low temperature and dense cloud. If we have lower temperature, lower dense, we have lower Jeans mass. And Jeans length and Jeans mass depend on temperature and density, as you see here. Here, we say that the gravity tries to pull material in and pressure tries to push material out. Here you see the time to collapse, or we call it free fall time, T(g), and gravitational acceleration, G, and time to collapse, Tg, here you see. And just pay attention that if we have the denser regions, it collapses faster. It doesn't depend on the size. Also, you know that pressure waves travel at the sound speed. As we talk, for example, here we talk and we have sound speed. With sound speed, my words go out and you can hear. Then for ideal gas, we have sound speed of this, and sound crossing time, as you see. And just pay attention that if we have faster for a smaller and it is hotter regions. And here you see the ratio of time scales and Jeans length. If you have larger clouds are more likely to collapse. Here in the left-hand side that we do not have collapse, it means that pressure wins. We have pressure and gravity. In here, pressure wins, and in here, gravity wins. And this is the equilibrium line. And then the best condition that the star form is that the gravitation working against the pressure. If we have less density, we have less gravitation. If we have more mass, we have more gravity. If we have less kinematical energy, we have less radiation. So radiation works against gravitation. And it means the cloud must be cold because we don't have thermal energy. Gravitation only depends on mass and density and length. But gravitation does not depend on temperature. But on the other hand, radiation depends on temperature. Here you see the different process. For example, in here, you see that it takes, we have just molecular cloud, its core. It takes around 1 million years. We call it pre-stellar dense core, and the temperature is 10 to 20 Kelvin, and it is a very low temperature. We do not have disk, and we do not have radiation of disk or any flux of disk. And then we have formation of central protostar object. And it takes, you see that we have a protostar, young accretion protostar, and temperature is less than 70 Kelvin. And the mass of the envelope or here is more than the mass of the protostar. And here we have protostar, and these are molecular clouds, that they are dense and separate in fragment in two pieces. We have gravitation and radiation, or jets we call them. And then in here, you see that the radiation of the disk dominates of the radiation of the protostar. And it takes 200,000 years and the temperature is 70 until 650 Kelvin. It is more than hotter. And we have disk, as you see here, and we have the radiation of the disk, and also we have the black body of the protostar. So we have the radiation of the protostar or jets, and we have the gravitation related to disk. And here we have birth line for pre-main sequence stars. That is, radiation of the protostar will be larger than the radiation of the disk. And here you see that it takes around 1 million years. The temperature is 650 until 2880 Kelvin. And the mass of the disk is around 0.01 of mass of the sun. And you see the radiation of the disk is lower than the radiation of the protostar. And then in here, you see that we do not see any disk or the material of the disk accreted by debris and planets, and it takes around 10 million years. We call them weak Tauri star, and temperature is more than 2880 Kelvin. And the mass of the disk is less than the mass of the Jupiter. Now you see the radiation of the protostar is very high, but the disk radiation is very low. Do we have any disk here or not? It's the question. And we know that we do not see any disk in main sequence star because they are greeted by planets and debris. Here is the other way of telling of this. And you see here for class 0, we have molecular cloud and gravitational collapsed molecular cloud. But we do not have any disk, just we have black body radiation of the molecular cloud, which is more dense and it collapses. And then here you see that we have protostar with infalling envelope. We have disk and we have infrared radiation of the disk, but the protostar radiation is lower. We have more gravitation, the jets are lower, but we have jets and we have gravitation, and we have material around the disk. And then we have pre-main sequence with a thick disk, as you see here, but we do not have material around the disk. And we have more jets. We do not have gravitation as here. And the radiation of the black body is, or protostar, is more than the radiation of the disk. And here you see that this is very low. It is very low. The radiation of the disk is very low, and most of them accreted by planets and debris, as you see here. And we call it diskless pre-main sequence. Then in here we have protostars evolve into main sequence stars. As you see, properties infalling protostar. These are the sketch of them. Here the age, as you see. Here is infrared class. This, if they have disk or not. Here, for example, if we have disk, we have thick disk here. Here we have also a thick disk in class 2. The age is around 10 to the power 6 until 10 to the power 7. Here we have thin or non-existent disk in class 3 with the age of 10 to the power 6 until 10 to the power 7. And but here, possible planetary system, we have weak X-ray, and we do not have thermal radio, and but we have non-thermal radio. Non-thermal radio is radio comes from magnetic field. And for class 3, we have not non-thermal radio. We have non-thermal radio, but we do not have thermal radio. It has a strong X-ray emission, and also for the others. For example, for this one, we have thermal radio, but we do not have non-thermal radio or magnetic field. And then in here, you see that Hertzsprung-Russell diagram. This is x-axis for surface temperature. Here is hotter stars, and here is colder stars. And this is the luminosity for y-axis. And these stars are less luminous, and these are more luminous. And sorry, these are less luminous, and these are more luminous. Here is main sequence, hydrogen fusion. And you see that in here, if the mass, if we have more mass, the star, if we have more mass in a star, we have the star leaves the main sequence faster. But if we have less mass star, it leaves the main sequence longer. As you see here, for example, for this star that it has 15 times of mass of the sun, it takes around 10 to the power 4, which is so faster to leave the main sequence. But here, for example, we see 0.5 of mass of sun, and it takes longer years to leave the main sequence. So as I said, if we have more massive stars, it leaves the main sequence faster. If we have less mass star, it leaves the main sequence later. And here you see it again. Here we see the Hertzsprung-Russell diagram. Maybe we can ask how we can understand, for example, the star in here. It's a young star or cold or old star. Is this star in here? It moves it leaves the main sequence, or it's pull into the main sequence. The pull and push is a question, and how we can understand the between of them. We can say that if we have young stars, we find the disk and we see flux in infrared. But if it is an old star, we do not see any disk around it, and it has no black body radiation and no disk radiation. So we understand that if it is young stars or old star. Thank you for your attention, and see you next time. Bye.